Hey chemists, welcome back. In this stoichiometry lesson, we are going to look at chemical reactions, how reactants turn into products, how we use these whole number ratios in stoichiometry problems, and just how to classify some reactions. First, some vocabulary words. The chemicals on the left side of a reaction arrow we call the reactants, and the one on the right side we call the products. We have these things that are states. I'm sure you know this from your intro chemistry class. G is gas, L meaning liquid, S for solid, and AQ for aqueous, meaning dissolved in water. I actually learned recently sometimes you'll see the state X, which actually means crystal, a highly ordered solid form of some substance. Pretty rare, that one, but that's what crystallographers apparently use when they write chemical reactions in terms of a crystalline form of a solid as opposed to an amorphous form. Every time a reaction occurs, bonds break on the reactant side. Bonds break and absorb energy. That is always true. And then on the product side, products form, I should actually say bonds form, and release energy. And we have a way of looking at the net energy change, but there's always an absorption and a release of energy as you change the reactants into products respectively. What we have the ability to see the net outcome. Is there more that's absorbed or is there more that's released? That's related to something we're going to do later on called delta H, the change in enthalpy of a reaction, but we will get to that later. So let's classify types of reactions. It's useful for chemists to talk about them in terms of the way they're classified. You might have learned in your intro class that when you have multiple compounds becoming different compounds, that's a double replacement reaction. A hydrocarbon plus oxygen making CO2 and water is a combustion. The fourth one, an element plus a compound making a different element and a different compound, is a single replacement. If we have one thing turning into many things, that's called a decomposition. And then the opposite, if you have multiple things becoming one thing, we call that a synthesis. And those terms are still valid. However, we're going to use some different words to describe these. This first one, which makes a notoriously insoluble solid, aka a precipitate, we call a precipitation reaction. The second one, HCl and NaOH, that's the reaction of an acid and a base, so we'll call it an acid-base reaction. And the remaining four are actually all examples of oxidation-reduction reactions, what are called redox reactions. So we'll use these terms, and we'll use these terms, so it's just important to be familiar that they both exist. That's really the point. So for the rest of this, let's look at how we balance chemical reactions. Balancing means changing the coefficients that we see in front of the chemical species, so you have the same number of each element on each side of the reaction. So here we have 2 carbons in this ethanol molecule, so I need 2 carbons on the product side of the arrow, so I'll put a 2 in front of CO2. That's the only place they show up. There are 6 hydrogens in this ethanol on the reactant side, and the only place H shows up in the product side is water, so I'll need a 3 in front of the water. Notice I'm not changing the subscript. You can't do that. That changes the formula and the identity of the substance. We're not changing the identity. We're just changing how many of them will form in this reaction based on one of them reacting. I intentionally leave elements that appear by themselves last, if that's possible, because then when I put a coefficient in front of it, it doesn't affect anything else. And I'm doing that to other things along the way. So we now have 4 plus 3 oxygens, if I count all those up. I have 1 from the ethanol, so I need 6 more from the O2. That means I need 3 in front of the O2. And you can put a 1 in front of the ethanol. If you leave it blank, it's implied that it's there, but if you want to for today, that's a perfectly good thing to do. Let's do one more, and then I'll have you try the two without me, and then we'll see how you did. So here's ammonium dichromate decomposing into 3 other things. Looks like we have 2 nitrogens on the left, and I already have 2 on the right. I got 8 hydrogens on the left, so I'm going to need 4 in front of the H2Os. We have 2 chromiums and 2 chromiums. We have 7 oxygens, and then I have 4 for the water, plus 3 for the chromium. This is good if I just put 1s in front of everything else. So I'm going to do that. 1, 1, 1, and it's balanced. So I'd like you to hit pause and see if you can figure out the correct coefficient ratio for the remaining 2. Okay, let's see how you did. So if I just go left to right, nitrogen, I like to start with things that only appear in one spot on each side of the arrow. There's 1 nitrogen becoming 1 nitrogen, so I will leave it as 1s for now. There's 3 hydrogens here and only 2 over here, so I'm going to use a fraction to temporarily force balance this and put a 3/2 in front of the water. Now I'll check oxygen. I have 3/2 oxygens plus another 2/2 oxygens, so I have 5/2 of an oxygen on the right-hand side. And I'm going to use another fraction. In this case, I'll need 5/4 of the oxygen on the reactant side. Now, technically that's balanced, but we always normalize it to make whole numbers. So I see this denominator of 4, so I'm going to multiply everything by 4 across all the coefficients. So that means 4 ammonias become 5 oxygens and 4 nitric oxides and then 6 water molecules. That use of a fraction is just personal preference to temporarily balance things, and then you just normalize it at the end. And then lastly, we've got a propane molecule, C3H8. I'll need 3 carbon dioxides, 4 waters, and then that's 6 plus 4 oxygens is 10 oxygens. So that means I need 5 O2s, and the 1 C3H8 I can just leave as is. So now that we've got that, let's learn how we use these ratios in stoichiometry problems. In fact, the first one has to do with that reaction right above. Propane reacts with oxygen, there it is, to form carbon dioxide and water. And I want to know what mass of oxygen will react with 66 grams of propane in this combustion. So how many grams of O2 given 66 grams of the C3H8. So we're going to use dimensional analysis to get from this unit to eventually my grams of O2. So as we've been doing in this unit, the first thing I'm going to do is convert it into moles. There's 1 mole of C3H8 per, if you actually add up 3 carbons and 8 hydrogens, you get 44 grams of C3H8. Now we're in moles of propane. I want to get into grams of oxygen. Here's the one new thing we get to do. That 1:5 ratio of propane to oxygen is not just a molecule ratio, it's a mole ratio when you scale it up. So there are going to be 5 moles of O2 for every 1 mole of C3H8. Notice I'm writing moles of each species, not just the word mole, because now that we're talking about a reaction, I got multiple moles of things, and it's important to keep track of which species you're talking about. So keep it in your dimensional analysis. We're almost done. For every 1 mole of O2, there are 32 grams of O2, and then I can multiply this out. Let's see, 66 times 1 over 44 times 5 times 32, you get 240 grams of O2. Looks like they had 3 sig figs, so I'll just put a decimal point, and that makes that 0 significant. So that's the only new thing. It's this mole-to-mole ratio that lets us go from the moles of one substance to the moles of something else. Oh, whoops, I actually typed it wrong there, didn't I? This is 1 mole of... Oh, no, that's right. Sorry. This one new thing goes from moles of one substance to moles of another substance. Everything else is really the same. Grams into moles and moles into grams. So hit pause one more time and see if you can do part B and then question 28 from these word problems. All right, B is talking about the same reaction. This time they want to know the mass of CO2. given the same amount of starting material. So the beginning of my dimensional analysis is going to be exactly the same, 66 grams of C3H8. I'm still going to convert it into moles. There's 1 mole of C3H8 per 44 grams. That's just from adding up 3 carbons and 8 hydrogens. But now I want to get into my mole ratio of CO2. There's 3 CO2s for every 1 propane. So this becomes 3 moles of CO2 for every 1 mole of propane. And lastly, let's get into grams. 44 grams is how much 1 mole of CO2 weighs. That's very fortuitous. You'll notice the 44's actually cancel. So all I have to do is take 66 and triple it. And when I do that, 60 times 3 is 180, plus another 18. Who needs a calculator? 198 grams of CO2. Okay, let's check 28. 28 needs a chemical reaction, so hopefully the first thing you did was figure out lithium hydroxide reacting with carbon dioxide to make lithium carbonate and water. Let's write that. Lithium hydroxide plus carbon dioxide. This is one way of removing CO2 as a solid lithium carbonate. It's hard to do on scale, but in theory you could use it to get rid of carbon dioxide that's excess in the atmosphere. That's not balanced. I need a 2 in front of the LiOH, and that's it. Now it's actually balanced. Now they want to know how many grams of CO2 given 48 kilograms of lithium hydroxide. Now, if you converted this into grams by multiplying by 1,000, that's still correct, but I'm going to show you a little trick that sometimes is useful. You can keep the kilo and convert it into moles this way. There is 1 mole of lithium hydroxide per 24 grams of lithium hydroxide, but you could scale both of those up to the kilo. There's a kilomole of lithium hydroxide per 24 kilograms of lithium hydroxide, and you can keep going. Your mole to mole ratio can be kilo to kilo. There's 1 kilomole of CO2 for, 2 kilomoles of lithium hydroxide. And then there are 44 kilograms of carbon dioxide per 1 kilomole of carbon dioxide. And if I look at what that does, let's see, 44 divided by 2 is 22. 48 divided by 24 is actually 2. So this is 2 times 22, and you get 44, but your units are kilograms of CO2. If I turned it into grams, that'd be fine. It would just be multiplied by 1,000. So you didn't have to use that kilomole, kilogram trick, but I think it makes the numbers easier to look at so you don't get lost in these thousands of grams and thousands of moles. So the one new thing was essentially getting that mole to mole ratio that we used from the balanced ratio of coefficients in these different types of chemical reactions. And we're going to use this all year long.